Hi everyone, welcome back to ChemHelp ASAP. In today's video we are going to talk about real gases, but first I want to talk about a concept called STP. Now STP is an acronym. It stands for Standard Temperature and Pressure, and we use this with ideal gases. Now first let's define our standard temperature and our standard pressure. Our standard temperature is 0 degrees Celsius. Our standard pressure is 1 bar, although often you will also see standard pressure at 1 atmosphere as well. And 1 bar and 1 atmosphere are close enough that these are just about interchangeable. Now, the important thing is that STP, because we have a temperature and a pressure defined for our real gas, it means that we know what the volume is per mole of that ideal gas. And that is called the molar volume of an ideal gas. This is really handy when we have reactions involving gases, because what we can do is we can convert between volume and moles very easily. And obviously when we're dealing with reactions, we want to be dealing with moles. Now, an ideal gas at STP has a molar volume of 22.4 liters per mole. Now again, this is a very handy conversion factor when we need to know how many moles a certain volume has of an ideal gas, but I do want to caution you, this is only used when that ideal gas is at STP. So if you are at a temperature or a pressure that is not the standard temperature or pressure, you are going to have to use ideal gas to calculate either volume or number of moles. Now that we know what STP is, I do want to jump into real gases and how they deviate from ideal gases. Let's get started.
So far, we have assumed that all the gases we've worked with have been ideal gases, but not every gas behaves ideally. So let's talk about conditions where real gases behave most like ideal gases. Before we look at any plots, we are going to define ideal behavior. So here I have written my ideal gas law. I am going to divide both sides by this term here. This is my next step. Of course, the right side of the equation simply goes to 1. So now I have PV over nRT equals 1. This is the behavior of an ideal gas. So let's look at a plot with different temperatures. So here is our plot. Our y-axis is our PV over nRT. That is our ideal behavior. And on this plot, our ideal gas should give us a horizontal line right here. Of course, these are real gases, so they do not give a perfectly horizontal line. But which ones get close? So you can see I have several temperatures plotted. My purple line is 173 Kelvin, and you can see I deviate strongly from ideal behavior. The green line is 298. I'm getting a little bit better with the green line, but you can see my 873 really starts to look horizontal. So as temperature increases, real gases start to behave more and more like ideal gases. But what happens with pressure? Still keeping our ideal behavior, PV over nRT equals 1. Here is a plot showing high pressure. Again, my y-axis gives us PV over nRT, and my ideal gas should give a horizontal line there at 1. Here are several gases. My carbon dioxide probably gives the worst in terms of ideal behavior, but oxygen looks like it's giving the best. But this is at fairly high pressure here. Let's see what happens when we take this plot, but we drop the pressure. So here is a similar plot, but with very low pressures. And notice how many more of my gases are behaving much more like my ideal gas, which should give a horizontal line at 1. So real gases at low pressure will behave more like ideal gases. So while no gas behaves perfectly like an ideal gas, if we combine high temperature and low pressure, we are going to get the closest to ideal behavior.
Whenever you're using ideal gas law or you're using maybe the molar volume at STP, it is important to keep in mind that we are always assuming ideal behavior. Now, that assumption may be good and that assumption may not be good depending on our temperature and pressure of the gas. But we always do want to keep in mind that real gases are not necessarily the same thing as ideal gases. I hope you found this video helpful, and thanks so much for watching.